Okay.
Okay, gang, stargazers are us. We are closing in, ladies and gentlemen, on the start of our 6th year of the Astro Hour. My name's Ronnie Heron, your proud host of our Santa Barbara, California Club's weekly vlog podcast called the SBAU Astro Hour. It's all for the Santa Barbara Astronomical Unit, cosmology, telescopes, and astrophysics, all based at our Santa Barbara Museum of Natural History. As longtime members of SBAU, the five of us left here on the Zoom screen all love this stuff, and we relish getting together every week to talk about astronomy, the real fun science, and we're the fun club. You find our website, sbau.org. You find us meeting at the museum first Fridays of the month inside, our second Saturday star parties for now outside in the dark. Sundays, we're out at the Palmer Observatory for looking at the sun, and inside the plush, warm, and comfy Gladwin Planetarium, ladies and gentlemen, for incredible sky shows. Now let's talk about these timely topics for number 260 program, February 16th through the 22nd, 2026 of the SBAU Astro Hour. The Hubble scope captures a dying star out in Cygnus the Swan, and heavens, another star collapses into a black hole inside our neighbor galaxy Andromeda. We got the night sky lineup of the planets in 2 days to talk about. We're going to focus on the Coma star cluster, not to be confused with the Coma cluster. And so far, none of us on screen have had a coma yet or gone into one. We're going to analyze and discuss astro cameras, big time, covering the very fascinating photon detection basics. Now we meet the gang in charge. Commander of the Starship becomes our weekly source of the talking points, professor of all, if you will, and he's got many friends watching us. Jerry Wilson, beloved president, good
Good
morning.
morning, everybody. And good morning, Joyce and Calvin and Riley, my grandkids.
All right, Riley, Calvin, and Joyce, you better be watching. And Pat is there, right? Your lovely wife. She's such a kick.
Pat's downstairs dealing with the cleaning lady.
Okay,
Cat
you got
and
a
I are
cat.
locked in my office.
That's the first lady of the club, Pat Forgy. Our SBAU outreach is an incredible man named Chuck McPartlin in front of the Ukrainian flag, also married to Pat McPartlin, who happens to double as our merchandise manager and incredible treasurer and sells stuff before the meetings. And doggone, what a couple. Also joining us on screen, Tim Crawford, resident lens and telescope expert, longtime SBAU member, and joins me in asking a lot of silly, sometimes stupid questions.
You got it.
But you're going to work on an incredible program, a little half hour of your own take on cosmology in December, aren't you?
I think so. I think so.
Okay, on the last minute, I'll get 12 people wanting to be the other half. And speaking of our last half, here's Tom Whittemore, our newsletter editor, who misses greatly his Westmont College years of teaching, but that's all right. You got to retire sometime. Everywhere he goes, he smells like sourdough bread, and all of us want to get on the list.
It's a fun star party up there.
What?
It's a fun star party.
Yeah, it's a good sight, huh, Tim?
Yep, third Fridays. I enjoy it.
Yeah.
How many pair of binoculars do you own, Tom? You must have as many of those as you do lens.
No, just one pair. Just one pair.
Just one pair. Okay.
Yeah.
Well, let's do the sillies. We start every program. This will be number 260, and in 2 weeks we start our sixth season. Just love getting together here. We've lost one of our members in mid-December, but these are the silly things that Jerry Wilson forwards to us, the tunes, I'll call them. And some of them are stick figures. Most of them are science oriented. A lot of Larson stuff, far side. But here it comes. We'll start this program off with some laughs. And I always can't wait to get them every week. Ah, the man walking through a maze-like office of cubicles runs into a rat. Jerry, what does the rat say and why? Did I lose you?
Oh, this is, the mouse is going through the maze and he sees an office worker walking by and he goes, "Dude, you found the cheese yet?"
Oh, I didn't get this.
Really? You didn't know that was that was late? Those places are laid out like Rat's mazes?
Yeah.
I thought it was a giant rat.
Well, giant rat, giant mouse, whatever.
Yeah.
This cartoon here is about when I got single again and wanted to start dating carbon atoms, and they wouldn't have. You want to tell us about this, Chuck?
Just somebody pointing to a chart showing fossil bones that have been found, and then a graph of the apparently spectroscopy of the contents of the bone says the high carbon content of the skeleton indicates that this individual lived less than 13.6 billion years ago after the first round of stellar nucleosynthesis. And so
So
it's
that's
called
the most
cosmologist
accurate
carbon
that
dating.
cosmologists can get.
Yeah.
Is there such a concept as stellar nucleosynthesis?
It's a
That's
joke.
where elements come from, Ron.
Yeah.
Yeah.
Oh, you mean the exploding, the upper elements when it explodes, the others up to iron?
Yeah, the carbon in the bones they found had to have been produced after there were stars.
Oh, okay.
Mhm.
It's a good
Okay.
stick figure joke. This one I don't. Was this? Who wants to guide us through this? Tim, you want to tell us?
I'll try it. I haven't seen these. Eureka, I've discovered the origin of the universe. Glow in the dark ceiling decals.
Pretty good.
Okay.
They're there with a telescope doing public outreach. And
Yeah.
over here it says, when was the last time we've been outdoors?
Oh,
Oh.
I see. Okay, it's one of those.
But they're looking
all have those
obviously
on our ceiling.
at these glow in the dark stickers that somebody's put on their ceiling.
Yeah.
Got it. The bedroom. Now this one you're going to have to explain, Jerry.
That's an easy one.
Yeah.
Drilling for mercury? You don't drill for
That's
mercury?
the element mercury.
That's the element
Drilling
mercury.
for, yeah, H.G. Wells, right? The author. Drilling for
Oh,
mercury.
I got it.
Oh.
Element
You
number
guys, you're experts
78.
at puns.
Yeah. It's element
That's
number
like-
78, Ron.
Oh, that's like iron is Fe. It has nothing
I
to
didn't
do
I
with it.
didn't get it. It's right in front of me.
Yeah. H.G. Wells.
Oh, there's one right in front of you too.
Uh-oh.
All right, somebody's gonna have to explain this one. Is that Japan's flag? I don't think so. Theirs is red or yellow, isn't it?
No, this is the exact scale, 1-to-1 illustration of a 5 solar mass.
No, 5 Earth mass.
You're right.
5
5
Earth,
Earth mass. Um, what's the P? Black
Primordial.
Primordial. Thank you.
Okay, well, that doesn't explain anything to Tim and me. I'm sorry.
Yeah.
No, if you turned the Earth 5 Earth masses into a black hole, this would be its actual size. You could put your hands around it. You wouldn't get them back, but you.
Yeah.
On our screens is the exact size of a black hole if we collapsed.
Well, if you printed that image on paper, you can zoom it on the screen.
Yeah.
Okay, I'll buy that. Not a big laugh, but it's interesting. That's fantastic, actually. Okay, Jerry, tell us.
The newest space news. Astronomers have found the first known system with a main sequence star orbited by a 5-pointed one.
Are there lenses that give you 5 points? Aren't they even numbered, either 4 or 6?
It's just a graphic design. It has nothing to do with anything.
Okay, so mankind came up with 5 points, but it really isn't represented in space.
I think a three vein spider might have 3 spikes.
Really?
I think.
Due to a focusing of a lens?
I'm sure somebody could come up with a way of doing it.
Yeah.
Might be complex.
Okay. Okay, that got us in a light mood. Now let's go to the light
Now,
side.
should we go to the biggest one, the cameras, and do that first?
I
Sure.
love
Otherwise, we might get cut off partway through it.
Okay. if you
goodbye
want
me, boy. I'm waiting for this one.
Darn, Jerry, I was going to tell you guys we saw Mercury 2 nights in a row last week.
Ah,
Oh, okay.
Yeah.
drilling
in
for
gaps in the
Mercury.
clouds.
You'll
Yeah.
get it. You'll get your chance.
Oh, that's okay. It's just it's easily visible in the southwest.
Is that right?
The moon's going to be going by it. That'll make it
Yeah, that's
good.
right. That'll be interesting, huh?
Okay.
Okay, this little simple diagram Yeah, I know. This is actually an infrared detector cross section. The we make these for astronomy, but the visible band ones are just the same, but they're made out of the same material, silicon, silicon, silicon. This one is made out of cad zinc telluride, which is transparent to infrared light. And here the light comes in, and the light hits the band structure in the absorbing layer. And this is the first of the two-step process of detecting photons. The photon comes in and it creates an electron-hole pair by knocking an electron away from its atom in the crystal, and it knocks it up to the conduction band, so it can now move around. And the hole stays here, but it can also move around by being filled with an electron, and that appears to be a hole moving. But anyway, you get an electron-hole pair, and these things mill around for a few microseconds, and then they recombine. And that's called their mean lifetime. Now, the
When you
trick
say a hole pair, do you mean a HOLE or hole as in
That's
WHOLE?
right, Tim.
Hole, as in a hole. There's a hole in the ground.
There's
Yeah.
a hole. Yeah.
like here's the shovel full of dirt you dug out of the ground. It leaves a hole behind, and it leaves the electron. In the
Okay,
electronics,
okay,
both
okay.
the hole and the electron are mobile.
Okay.
So now what happens is they stay apart like this, and then they go back together in a crystal, and they either re-release the photon, or they take the energy and add it to the crystal, and the crystal gets slightly warm, which, by the way, is another story we're not going to get into about how to detect that the photon was there. But what you need to do is, before these things recombine, you need to subject it to an electric field to separate the two, and then make them recombine, around a circuit. And when they go around in a circuit to recombine, that's when you detect them. So it's a two-part thing, and that defines the quantum efficiency of the detector. The quantum efficiency of the material times the collection efficiency. Now, in this case, this has got a little extra jolt in it because it's red material. This is called a crystal field, but we don't, and it only acts on the hole. It doesn't act on the electron. But in silicon, that's not true. This is a flat line, and there's nothing to make it move by itself, except if you create a lot of them, the population density kind of squeezes them over toward this region here called the depletion region. It's a boundary region between an N and a P type semiconductor, and this is where there is an electric field. If you get your electron hole pair over to this depletion region, then the charges get separated, and then they go around the circuit, and you detected it. Any questions?
Are you describing basically what the new digital photography is versus the old Kodak with its silver in the lining and all that?
Yes.
That was a different process that is more complicated. Here they had this material here that absorbs the light would be a silver halide molecule. And the light comes in and it hits the molecule and it changes a bond. So that the thing, when it gets a chemical in it, it changes the color of the material. And then you see that as a dark spot or a negative black.
But what Ronnie said is true. This is the replacement for that. This is what
Yes.
took over now.
Yes, this is solid state detector.
Huh. And I can remember them saying that, no, we'll never be able to replace this.
Okay,
The only way
the
we can get
takeaway is 2 steps to detection. 1,
Okay.
you collect the photon. 2, you collect the electron hole pair. If you don't do both of those, you didn't detect anything. So you have to design this thing with thicknesses and field strengths and bias and doping levels in mind to get that to happen.
Did I miss what the H and the E stand for? I know they're valence or plus.
That's hole and electron.
Yeah,
Right.
this is an electron which has a minus charge, so it's electron with a little minus sign. The hole has a plus charge because it was neutral, and now when you took the electron away, now it's appears positive.
And Ron, the photon comes in with zero charge, right? It's photons. So it has to create something that has net zero charge. And that's why you get a hole in an electron.
Really? What is
It's just one way
MWIR?
of looking at it. Okay.
What does MWIR stand for?
It's infrared.
Medium wave infrared.
Yeah,
Yeah.
mid-wave IR. This is short-wave IR.
Yep.
And the yellow line represents.
And Ron, eventually you're going to collect those electrons and form something called an image.
Yeah.
So,
Yeah, this one.
but Jerry's in charge of this one.
What you're going to get is you're going to get a single, these electron hole pairs, once they're separated, you'll collect the electrons in a potential well, like a capacitor. And then when the shutter closes, you count the number of electrons you have. And that's the signal level. So it's a single number that goes through the electronics and it gets converted to a digital number.
Which is like your level of darkness or your level of brightness.
Yes, exactly. 0 is dark. Up at full well capacity is not only a signal, it's saturated. Want to avoid both of those, or each of those.
So what we're looking at is not just in Astro cameras, it's in everybody's cameras. They buy at a Photoshop and take home and take
That's
pictures.
right. It's in your cell phone. We'll get to that.
It's digital cameras.
Yeah.
Got it.
Now this is an MIS set of a small section of an array of MIS, metal insulator semiconductor. This is the semiconductor here, which is a P-type silicon. It's separated here by an insulating layer. And then here there's a ground contact. This is a deposited metal. You put a bias on this contact and it collects negative charges down here. So the light is coming in from the back and it creates these negative charges at this boundary. And then once the picture is taken, then you walk these voltages down the line and it will hand off. This is called a bucket brigade device or a CCD. And it will hand off this collection of charge to this plate, then to this plate, and you'll get them out at the end. And that's the read line for a CCD.
I'm sorry, guys. I'd missed a lot of this. I went offline for that whole time.
It's been very wholesome, Tim.
Yeah.
That's right. I learned a lot, Tim, without your help.
Thanks, Chuck.
We're merciless.
There's a term I haven't heard you use, and I'm wondering if you could clarify that. And that term is pixels. Is what you're describing inside every one of those jillions of little pixels, or is it something broader?
Yes, I'm doing a close-up look at one pixel.
Yeah.
Now,
one pixel.
Yeah. Now,
in the old cameras in the old days, the Kodaks didn't use pixels.
They did, but they weren't defined by processing, by cutting up into these squares. They were defined by the molecule, and so they were irregularly positioned.
Kind of randomly spaced.
Right.
And silver is gone.
Yes.
Now, there's no silver in this.
So I guess what I'm missing is, and I really wanted to hear it, is that the silicon chip, that's what's actually gathering the photons and turning it into electronics.
Yes, that's correct.
Okay.
The photon interacts with these substrates you put down and generates electrons, basically, that you count.
Okay. I remember when Bob was a Piontek. Remember Bob Piontek? He developed his little fish camp cameras, and he was doing all this stuff. I don't know if they've quit doing that, but it's fascinating.
Yeah, thank you, Tim, for pronouncing his name correctly in Polish. It means Friday, the fifth day, Piątek.
Yep.
Yeah.
Okay, this is showing.
Here it is. That's how you move them, Ron.
This is showing the CCD in operation as it passes the charge down across these things. Now, the largest CCD chip I ever held was a 10,000 by 10,000 element with about 8 readout lines in it. And they were made for a Mars orbiter.
Whoa.
Now, okay.
Well, I hope there's not a test on this because I probably won't do well. Yes.
I'll correct you.
Oh, I'm sure you will. Why did you have to leave us, Tim? Something happened? Your
Yeah,
phone-
must have been some disruption here in the house, and
Oh, what
Karen,
just
Karen
happened?
walked Karen walked in and said that our Wi-Fi just was gone.
Well, that's when those things strike right in the middle of our program.
Well, there are a
Oh,
bunch of arcing wires and other problems around town from the storm.
Yeah, was fairly intense this morning.
Yeah.
Okay, this is a cross section of an alternate device. This would be a CMOS. The difference between
Oh.
a CCD and a CMOS is in the readout, not in the way that things are turned from photons to electron hole pairs. But rather than have the whole area under an electrode in a field region, here we have a junction between a P and N type material, and this produces an electric field. So light comes in from the back, creates its electron hole pair magic, and then the population density causes it to drift up here and bam, gets separated. So the electrode here, the anode takes it off to a readout circuit, and the cathode takes it out to a readout circuit, to the other side of the readout circuit, where they are stored for a brief period of time on a capacitor, a feedback capacitor in an amplifier. So this is a CMOS device. It's a photodiode. The other one is a CCD.
Okay, so at this point, Jerry, at one point, CCDs by far outperformed CMOS devices. Now they've caught up. Why?
Okay. CCDs and CMOS. CCDs are typically have a better fill factor. Now you'll notice that here there's nothing impeding the light coming through. The unit cell is this whole thing, and the light comes in and hits everywhere on it. So it collects all the photons. On this, the light you can come in from the back, and you can collect all the photons here too. But frequently the CMOS has circuitry. For example, here they have the AR coating on the top. So this is intended, because the ground here is a contact metal, that's opaque. So here the AR coating, the light comes in here actually into this active area for the CMOS. And it's got electrodes here and there, and that's in the way. So that blocks some of the light.
What is AR?
AR coating, anti-reflection coating.
Hmm.
When light goes through an interface, you generally account on 5% being absorbed, unless you put an AR coating on. And the AR coating has an index of refraction that's halfway between the square root of the index of refraction of the two interfaces, and it tones loss at the interface way down to less than 1% usually.
Wow.
Wonderful invention. So CCDs have a better fill factor. More of the pixel is used to collect light. CCDs have higher output uniformity because they go through the same amplifier, resulting in fewer artifacts. Now, a lot of people in our hobby call these artifacts noise. That's not noise. There's a lot of artifacts. I'll explain that in a minute. Dynamic range, CCDs generally offer a better dynamic range, making them superior in extreme lighting conditions. And they're used in high-end professional and amateur astronomy. The CCDs generally cost about twice as much as a CMOS camera.
Now, dynamic range is the ability to collect light at wider wavelengths?
No, its ability to see fainter scenarios and brighter scenarios in the same detector.
Okay.
See, if you're in the forest camping and you look out at the forest, you'll see the trees and you'll see the light going through the trees and you'll see the shadows of the trees on the ground. There is no camera that's made that can take that picture.
Yeah.
With showing detail in the bright parts and detail in the dark parts. Your eye can, but it doesn't work. It's not a dumb camera. but the camera can't because it doesn't have the dynamic range to do it.
Okay.
CMOS has made improvements. First of all, CMOSs operate between frames that can take pictures much faster. So you can't really do video with a CCD. So if you want to do planetary stuff, you need a video to keep the 10,000 frames you need to work with before Jupiter rotates out of the field of view. CMOS can't do it, or CCD can't do it. Integration, CMOS can include image processing amplifiers and digitization on the same chip. So it's used in cell phones, DSLR for planetary and deep space cameras. It works very well. And it's much cheaper. Yeah, go ahead.
I've noticed, like with for instance, the QHY cameras that we discuss on Tuesday nights, they have a CCD one and a CMOS one.
Yeah.
Now is because of, I'm wondering why, since it's a planetary camera, or is maybe one not a planetary camera and the other one is this.
You can use any camera for anything you want, but they're generally not suited well for what they're going to be used for. Someone just buys a camera, puts it on their telescope, and uses it.
Therefore, if I'm interested in the moon and planets,
Yeah.
CMOS for sure.
Yeah.
Okay, great. Thank you.
So this is a summary table. CCDs do row by row. It's slow. Power consumption is higher. Cost is higher, and sometimes much higher. It has a global shutter. It has lower noise. And that's not things like artifacts being confused with noise. This is noise you generally don't see. And it's best for high-end scientific work. Now, CCDs for scientific work come in class 1 and class 2 or class A or class B, and that has to do with the number of defects in the readout. So a class 1 will be, let me show you here. This is a class 1 QHY CCD with a big chip in it. And these come in either color or black and white version, mono version. This particular camera starts at $16,000 because it is a class 1. That is, in the central 25% of the chip, there are no defects. Outside of that central region, there are only single defects, no neighboring defects, no bad rows, things like that. Now, we don't need that. We do our processing, which corrects for all these bad things.
I see. I see. That's a whole lot cheaper.
They are a whole lot cheaper. CMOS, their individual charge transfer, it's fast. You go from the detector right to the readout, right to the circuitry. There's no wait for it to hand off the buckets. Power consumption is low because they're basically all capacitors, and there's not a lot of current flowing through it. Cost is much lower, mostly rolling shutters. Noise is higher, but it is improving. And in some cases, it's essentially equal to what you get for a CCD.
Is cooling factors better in the CMOS because of that less voltage going through?
No, it's the fill factor is better because there's less crap in the way of the light beam.
Okay.
Best by far is best for is consumer, video, and speed.
Consumer video.
Now this is a picture of a
Filter wheel.
yes, filter wheel on a CCD camera. This is actually a QSI camera.
Okay.
This one, it's on this camera, and I have 2 of these. They're ancient now.
Filter wheel, filtering stuff like the sun.
But this has a filter wheel on it.
No.
And because it's a monochrome detector, here there's no filter, so you can see the detector.
Ron, they take the images with all these filters and then combine them.
Yes, that's right. So then here's a red, green, and blue filter. So you take your picture here, say, and I usually take about a dozen 5-minute exposures for an hour and or a half hour. And then I go over to one of these and I take it again. So you got to take 4 exposures with this is, cameras are labeled like this. They're called monochrome. And you need a filter wheel to do color with a monochrome camera.
And this is also, Ronnie, a reason that I think these people are crazy.
Well, it reminds me of a revolver gun. They should call it a revolver.
It reminds me of a lot of time. And then they have to process it. Oh my God. These guys work a lot to get a
Are
picture.
these your pixels?
So this is a close-up of 1, 2, 3, 4, 5, 6, 7, 8 pixel, 8 by 8 pixels in a CMOS camera. And the CMOS camera has little filters on top of.
Well, it's a color camera, not necessarily CMOS, right?
That's true. Yes, this is and you're correct. This is a color camera. They call you at the consumer level, they're called monochrome or color. And this is the color one, right? And what they do is they put a little filter on either a red, blue, or green. And this is the commercial thing that's common in your cameras like Canon or Nikon and your cell phone. And this is called a Bayer filter. And so one of the first steps you do when you get this picture, because it's all gray, is you separate out the red, blue, and green into separate bins. And so each set of 4 cameras like this, and you notice there's 2 greens and 1 red and 1 blue. That's because the human eye is most sensitive to green. So to do the processing to put it together so your eye likes it, you have to have more green than red or blue.
Are these chips or are they, what are they?
Those are pixels. Pixels
Yeah,
on the
Pixels,
chip.
okay.
This is a small section of a chip,
Okay.
and each one has a filter on top of it like this.
Why are we looking at a picture with some of them not on the board? Why isn't it all laid out?
Just
see
to
what's
show you
underneath.
that there are the monochrome pixels underneath, really.
Yeah.
Yeah.
Oh, I see, got it.
So this one under this green filter, whatever light gets through to the detector underneath of it is only green light. The red light and the blue light is blocked. So this pixel gives you a green light. And then you put them together. Right. What you do to calibrate this, the ideal way, but a lot of people don't do it, is you find a star in the night sky that is a G2V star. That's the spectral class of our sun. And our sun defines white. So you take a picture of the G2V star, so it's not saturated with this thing, and you look at the ratio of red, blue, and green that it captured. And then when you get the red, blue, and green, you put them together in Photoshop in the same proportion as that star had. And that gives it the closest to what the star probably would look like if you were looking at it with your eye.
That's how you do it. Huh. So Photoshop allows you to put the percentages up there.
Oh yeah. So does I think every other software I've seen. I do it in CCD Stack too, and that it has to have the ratios.
That's interesting. That answers my question of one night at the workshop. I said, "Well, why are these colors? Is this how they're really representative?" And your answer was, "No,
No.
we're making them up."
Yeah. Now what we just showed with the Bayer filter is in your CCD in your phone, and these are good cameras. Some of them are big, like 14 million or 20 million pixels.
That's amazing.
Now a pixel is a picture element. Our hobby is sloppy, and they call a chip a pix. They call one of the little squares on a chip a pixel. It's not a pixel. It's NASA defines it as a detector sample. So that's the technical. That's why a lot of these things can be confusing if you come from the technical world.
I sort of had an idea that they were like little round balls of glass rather than cute squares.
No, they're squares.
They're squares on a checkerboard.
Some
I've
are
got one of-
rectangular, but yeah.
Yeah,
I mean,
they
you
can
know,
be
not-
rectangular.
Yeah.
I got
This
one
is-
of these, Jerry.
What?
I have one of these guys.
Yeah, this is from Teleview. These are the ways you get your phone onto a telescope. These clamps adjust and hold over this aperture, and then the lens on the camera fits, and there's a nose piece that fits here to go into your telescope.
Except they have to be a Teleview eyepiece.
Well, that's a detail.
Yeah.
Now, for example, this is a DSLR. This is a common entry-level thing. It's a CMOS camera. They're all CMOS cameras. Each camera has its own pattern of Bayer, so you have to figure out, which is easy to do, you start with the first pixel is in the upper left corner, just like you read. First it goes across and then down. So the first one is unit 1, and the bottom right is unit 14,000, 14,000, or 7,000, 7,000.
Wow.
Anyway, you have to figure out which is red, blue, and green, which is easy to do because each camera company uses a slightly different method. And there are new ones out that are called LRGB. So they have a one without a filter if you want to do real detailed processing.
Oh.
So here you put a nose piece on here and it sticks in your eyepiece holder. You set the camera on bulb, use a remote exposure timer to take a series of things. It's a hand paddle-like thing that you set it up for, say, 24 5-minute exposures. And then you go in and you watch old movies. So many have handy features, including live view with 10x, which is very easy to focus. There is, however, no focal plane temperature control, which makes dark frame subtraction very tricky. Now, and it uses a Bayer filter. Now, when you take this picture, silicon is a photo detector, of course. When light hits it, it makes electron hole pairs. But when light doesn't hit it, you get electron hole pairs from thermal emission in the film, in the detector. So you have to, most of the astronomical cameras, not the planetary ones, that differentiates planetary from deep space. And from this is that they're cooled. They have a Peltier cooler in it. So you're operating around 0 degrees centigrade to take the picture to suppress the thermal generation of carriers called dark current, not dark noise, but dark current. And these do not have that feature. So if you take a picture on a cold evening and then later you're taking dark frames at a different temperature, the dark current is exponentially different between the two. And so subtraction of one from the other is not going to get you a bad pixel subtraction. It's going to create artifacts in it. So it's tricky to do. You need to take and Canons will let you they will let you take a dark frame and then a picture frame right there together. That's the best you can do for it. But in processing, I use a dark pixel correction map instead of a dark pixel. Well, anyway, it's too complicated.
I'll say.
This is the nose piece that you would use on a
Camera.
DSLR, except here you have a T2 or T4 adapter to fit the bayonet mount on the camera. This is a CCD planetary camera. These are not cooled, but they're made for. This is actually, it's got a fisheye lens on it, so it's an all sky camera.
And it's saying it's CMOS here in the caption.
What's that?
The caption says CMOS.
Yeah, it is. Did I say C something else?
Yeah, you said CCD.
Oh yeah, this is a CMOS. This is one that would use for planetary stuff too. If you change this lens, which this just pops off and you put something on. These are commonly used for guiding or for planetary. You know, you got to take pictures quite a way because Jupiter goes all the way around in 10 hours and it goes halfway around in 5 hours. So if you spend a lot of time with a CCD camera, you don't have time to fiddle with the filters to take good pictures of Jupiter. This is a CCD camera. This is where this screws off and then you'd see the chip in there and it has a projection, a nose piece. And this is a screw in place for a guide camera. It has a little pick off mirror up there. So this is, if you have a larger scope, sometimes the guide scope and the camera flex and you get stars that are not round. So that prevents that with having a pick off on the camera. This is the CCD. It's that same CCD camera, with a filter wheel attached, how they look like. Some of them are very bulky. The one we saw earlier was a 5-position with 1¼ inch filters. This is a 7-position with 2-inch filters.
Ooh,
Big.
Yeah.
yeah.
And this is our beloved grade 1 CCD QHY professional level instrument.
So you said 16,000, you said?
Yeah, this was listed on the internet for 16,000.
Yeah, it's about 15,000 something over my limit.
At amateur astronomy conferences, this gives you extreme bragging rights in some people's minds,
I bet.
or extreme idiocy rights in other people's minds.
And you're saying this is CCD, even though it said CMOS? Everything on the top says CMOS.
This is
Typo, maybe.
yeah, it's just an error in my.
Oh,
Uh,
okay.
so anyway, this is
Noise,
this is what I was banging on about earlier. This
Yeah.
is, of course, Jeremy from I forgot the
cartoon.
Zits.
from
Zits.
the cartoon strip. And there's 2 definitions of noise. There's the physics definition, where noise is not a thing all by itself. Noise is only a stochastic fluctuation in a signal about a mean value. So if you see a voltage level and if you magnify it up, you'll see it's bouncing around a little bit. That bouncing around is the noise. But there is no noise all by itself. Noise has to be in something. It's some fluctuation of a random something. But in colloquial terms, we use it commonly, and amateur astronomers do this too, and it's very confusing. If you get a paper and the guy's trying to talk about how to get rid of the dark noise in your pictures, he's really talking about dark current, not dark noise. And it gets very confusing. And that's illustrated by this. You live next door to Jeremy, and it's Sunday afternoon and you're tired. It's your first real day off. And you're trying to take a nap on the couch, and Jeremy just got a brand new guitar next door. And it's not producing beautiful music. And we refer to that colloquially as noise. But that's not noise. That's a signal that we're not interested in. So you can take away that. You can record that noise with earphones that cancel that noise. By taking it away, you subtract a noise. So things that you can subtract out of the picture, which is virtually everything that we do when we process, that's not noise. The way you get rid of noise is you add more noise. And the signal to noise ratio, the signal goes up linearly, the noise goes up as the root sum square. So it doesn't go up as fast. So the more times you repeat the signal and noise, the signal to noise ratio gets better and better. So in a sense, you're adding noise to decrease the importance of the noise. But in our hobby, it's rampant. I even had a conversation with Sky and Telescope's chief editor about why they perpetuate this myth that a lot of our stuff, it's like planets and dwarf planets. A dwarf planet is not a planet with an extra adjective on the end of it, beginning of it. Now it's supposed to be something completely different. Noise is this temporal thing, but we talk about fixed pattern noise. And so that's something different. That's like a dwarf planet. It's not noise. It looks like noise, but you have to put the fixed pattern in front of it. And it's something that you can take a picture of and you can subtract it out. So that tells you it's not real noise.
Now, Jerry, in the software that you guys are using, blur exterminators, star exterminators, are they kind of using the same type of cancellation?
They are not. No, any noise you can see in a picture, like in the old days, we put our TV between channels, and you'd see this static in there.
Yeah.
That's real noise. That's changing in time. And it turns out a portion of that noise, I'm told, is the
Cosmic microwave background.
Yeah. So that's real noise. But if you take a photo of it, of that noise, you have a picture of that noise at an instant. But your picture is now not noise. It looks like noise, but it's not changing. When you do these pictures, when you take a subframe, say a 5-minute picture, and it's got speckles in it, and they may be captured noise, but they're not noise. You can take a picture of those speckles and subtract them out. So there are different ways of treating it because there is some real noise in there.
Okay. Okay.
So basically what you're doing, Gary, is telling us the difference between the audio noise and the visible noise, right?
No,
Oh, okay.
visible noise has a random pattern to it. That is, if you look, most of our devices are so noise free that you look at a pixel, you go up with a magnifying glass to your TV set, you're going to see the red, green, and blue pixels, but you're not going to see them flickering in brightness. There's no real noise in there. What you're looking at is if you see anything you think is noise, it's probably fixed pattern noise.
Okay.
Now, this is something that's a little, maybe a little off, but when you speak of this, it reminds me of when Dick in the workshop talks about in his processing that he can't process he can't use one software to process something out before he uses another one, or else you lose a lot of data.
Who's that? Who's Dick?
Dick Beam.
Oh, Dick Beam. Dick doesn't completely use noise right. He's developed his own nomenclature and his own way about doing things.
Yeah.
But technically, it's not exactly right, but he's right. I mean, his pictures work that way, but you just have to suspend the field jargon from the colloquial jargon.
Okay. It's also you guys go over it with me over and over and over, and it's amazing that some of it is sticking, but I think until you actually do it, you don't get it.
Yeah, once you start doing it, it's very clear
Yeah.
and it's very simple.
Well, it seems to me everything you were talking about had very little to do with that guitar player we saw in the cartoon.
Because that wasn't noise, that was signal.
Yeah.
Oh.
Yeah, signal you're not interested in, easy peasy, we can get rid of that. We just photograph it and take it away.
Are we going on to the other subjects now, past the
Yeah.
camera pixels?
Yeah,
Okay.
now that you know all about the cameras. Okay, this is a star in Cygnus, 1,000 light years away. It was taken by the Hubble Space Telescope. This is called the Egg Nebula because it has a yolk,
And it's dying.
and that's no yolk.
No,
And it's
yoke.
dying on us?
It's a bad yoke.
So it's throwing off. Now this is it really reason I put it in here because it was confusing me. This is a star that's becoming that's throwing off its outer layers. This is the end of a star, a dying star. But it's also creating this cloud of all of its products of fusion when it was more active. So it's creating this cloud of stuff, and this is going to become a protoplanetary disk or a protostar. It's going to become another star.
Possibly once it throws
Yes,
it off.
possibly, yes.
Huh.
They call it the first, youngest, and closest pre-planetary nebula ever discovered.
But see, that it's turning into a planetary nebula, which would be like the Ring Nebula or the Dumbbell Nebula.
Exactly. This is, yeah, they're the thrown off outer layers of that star.
But we see 4 plumes going out, 2 on each side.
And the reason it's doing this is due to a coordinated series of poorly understood sputtering events. So that's the conclusion of their paper.
Yeah.
And I will go along with that.
But it's not dying with a nova.
What's
Novas
that?
aren't necessarily a dying star, but yeah.
No.
Okay, I thought novas were the main ray stars.
No, that's supernovas.
Oh, okay. Well,
Nova's a car, Ron.
Yeah.
That's
Oh, no. Oh, no.
Nova.
It doesn't go. Doesn't
Yeah.
go.
Got it.
Now you lost me.
Okay.
Well, we got 10 minutes to cover the other stars. There's one being swallowed up by a black hole in Andromeda.
No,
And
no. It's a star that just collapsed directly into a black hole without going through a supernova.
Oh, yeah, yeah. I've
how's
heard
that
of these.
how's that different from what I said?
Well, there was not a pre-existing black hole there that ate up the star.
It became a black hole.
Yes.
Without
Oh.
without the implosion.
And we can tell. I mean, we can't see black holes in our galaxy, are we?
But the star just disappeared.
Okay, we're
Oh.
going to have to endure 2 commercials here.
Okay.
Can you
Oh,
see? Can you see the commercial?
yeah,
Oh,
you sure
yeah.
can.
Okay.
Yeah.
You might be able to click off of it early, the lower right.
No.
Sometimes I don't want to get too fancy with this software.
You're going to give us sound.
No, I joined it. It's crazy, right? Hey, let me call you back. I got to stand in a line. Even crazier is that folks stick with insurance that keeps them waiting around to find a claim.
Yeah, sometimes they don't offer the.
Oh, we don't need the sound.
Yeah.
Well, that's a long line on the bottom, that white line going across.
It's getting there.
I want to change my car insurance just from watching this. Love to squash that little lizard.
The gecko.
Looks
Yeah.
like a planetary here.
Okay, crank it up. Don't hear anything.
That's all
There's
right.
no sound. In
Oh, there is
Sweden,
no
I
sound,
can't
though.
hear you scream.
Oh my God.
What the heck?
Hmm.
They're in love.
God
Looks
bless.
like the Saturn Nebula.
Yeah. So this is the what are the nebula that it was called? Banana Nebula? What is it?
Not dumbbell.
The Egg Nebula. Yeah, the Egg Nebula is this part in the middle. And this is how they believe it formed. This is a
Hmm.
We're flying around it, looking at different aspects of it.
right. Yeah, it's not rotated at this speed.
Boy, that's really fancy. I really like it.
Chances are there's no life on any planets around it.
Not anymore.
Fascinating stuff, Mr. Prez.
Let's just see if I can get back in here.
There were just really, there was something I heard, like if Beetlejuice were to go supernova, that the views we'd have of Orion would completely change.
Sure, yeah.
There'd be no
No
more
shoulder.
armpit. Wouldn't have an armpit anymore.
Yeah.
We'd have to go
Big
with the,
crater.
we'd have to go with the Australian saucepan.
Yeah.
Okay, now this is
Wow.
The Coma or the Andromeda?
this is a nebula around when a star went toward its death. It threw off all this stuff, which is going to become a planetary nebula. And this is in the Andromeda Galaxy. This is not the Andromeda Galaxy, but it's in the Andromeda Galaxy. And this is a star that just simply winked out.
Is this an artist rendition or real?
Yeah, absolutely an artist's rendition.
Yeah,
Okay.
I think I say that. An illustration, it says an illustration.
We'd never be able to take a picture this clear from Andromeda.
Never say never.
This is taken by NASA's NEOWISE satellite and processed and interpreted by a team from Columbia University. The star is labeled M31 2014 DSI. It's about 2.5 million light years as Andromeda from the Earth. It's 13 times the mass of our sun.
Hmm.
Relatively lightweight by typical black holes forming standards.
It appears to be very bright and alive in the middle.
So this is similar to Betelgeuse, and is one of the ways that Betelgeuse might go for us. It might not form a supernova. It
Really?
might start sloughing stuff off and then just simply collapse into a black hole.
All that dust and gas is red, or they just decided to choose red?
It's artificial coloring. That's
Okay.
now this
Okay,
is an
there's-
interesting picture. This is a stunning image of the Andromeda created by an array of space and ground telescopes. It's got everything in there, including the kitchen sink. It's got X-ray images, infrared, visible, Planck, radio waves, ultraviolet, optical. This is a composite of virtually every wavelength that we have.
And 32 is the one, the companion galaxy below, and 110 is the blue one.
Hmm. And on Edwin Hubble's version, he wrote BAR on the right side, didn't he, somewhere?
Well, no. Well, it was on a single star. Yeah.
Yeah, that's what I meant.
Yeah.
Didn't you recall that picture?
We'll just run a little bit over here. Now, this is the morning. This is, I think, Thursday morning, February 18.
It's not, it's the night. You see
Oh,
Mercury.
yeah, you're right. It's evening.
Yeah, because we see Mercury. Venus is a little tough now,
Yeah.
but we've seen Mercury several nights last week.
Now, this one is, if it were, let's see, this is the evening, so the moon is moving this way. So the moon, if I go earlier, the planetarium software has them all underground. It jumps. But
Mhm.
right there is Mercury, right about to come out, according to this plot, out of transit or eclipse by the moon.
Yeah.
But I don't think we, and if you wanted to see the eclipse, that's early in the afternoon, and the
Yeah.
sky was too light. Actually, at 6 o'clock here in Goleta, the sky's way too light to do this.
Yes.
Mhm.
Yeah. Yeah. We see it more like 7, I think. Mercury.
That light already now?
Yeah.
Yeah.
Yeah, it's getting dramatic.
Wow.
And I believe Mercury is now going down and Venus is coming up. Sound good, Chuck?
I
Yeah,
think so. Yeah.
Yeah.
and
So-
Neptune and Saturn are up here.
Might be able to see them both in binoculars, huh?
Yeah.
And
Not with our sky, but
why, Tom, is Venus hard to see?
it's low.
It's just low, close to the
Right
sun.
here.
Mercury is a very easy pick off. Must be awfully bright. Must be still negative magnitude.
It says minus 0.6 here.
Okay.
Wow. I had to fiddle with this timing and stuff and position in order to get Venus to stand out behind these trees.
Right. You notice how Venus and Mercury show the ecliptic being, nice,
Uh-huh.
very much up and down, if you like.
Oh, yeah.
Mhm.
It
Okay.
seems to me all those red lines could make great stick figure cartoons if you just put some little sound things, little bubbles with their words.
Yeah. That's the great square of Pegasus there, Ron,
Yeah.
on the right. And then you see that the head of one of the fish just above the moon there. Right there. Okay.
Well, that looks like a long dipper upside down.
This feature right there, it should
Right.
have.
I always put that star in, Jerry. The
Yeah.
circlet. The circlet. Yeah.
It makes this thing look like an anvil,
Yeah.
but it's really a circlet.
And the other fish is not as dramatic. It's up there near M74.
Yeah.
Yeah. And then the little bow, Auretia, the knot, it ties the fishes together.
It's
All
a
right.
halibut up top and it's kind of sideways. So
So that's its one eye on top.
yeah.
Okay.
Or,
Well, I think that concludes us for today.
well, doggone, what a way, what a trip. I appreciate it. Thank you, everybody. Join us again, coming up our third Friday out at Westmont, and we'll have another great evening workshop tomorrow. And doggone, we don't know where we're going to be in the future, except I guess we'll be talked to about volcanism on the Friday, the 6th of March. In the meantime, everybody, thank you for joining us on the Astro Hour. We have a special way of saying goodnight, Irene. What would that
Asta,
be?
less nebula this week.
Yeah.
Great job, Jerry. Great job today, Jerry.
Or
Thank you.
Enjoy
do
the storm.
widzenia. Do widzenia.